Hello, everyone. I am going to tell you a very interesting story about aperiodic tiling and Penrose tiling, which is a kind of aperiodic tiling. Um, Aperiodic tilings are kind of there's this history of aperiodic tilings, and really I just want to there's an interesting thing about the history of aperiodic tilings, which is that they are arrived at in a way that is ridiculous compared to the modern understanding of how this particular one works. The original aperiodic tiling is some, I don't know, some set of 20,000 tiles, square tiles, just with kind of irregularly shaped sides. I mean, so I guess they're not really square, but mostly square. But the irregularities on the sides would only allow them to be pieced together in certain ways that was irregular. And there's some precise definition of what irregular means, but intuitively it just doesn't repeat. I mean, little ideas of it might repeat, but any thing that you see anywhere, you'll be able to find somewhere else a kind of slightly different thing than that. Anyway, and the reason they came about is because somebody had they had a conjecture that a certain problem of trying to piece together these tiles, they figured that if it was decidable, or that is to say, if it was undecidable, then there must be some set of tiles that go together only in an irregular way. He didn't think that would be the case, but his student apparently showed that it was. Anyway, so the first tiling was huge. And then that same student made it smaller, a lot smaller, 104. And then somebody found a lot smaller one, 40, only 40 tiles. And then somebody came up with just 6. And then Penrose comes along in 1973, and he also finds a way to do it with 6 tiles, but then he also reduces it to 2 tiles. And the 6 tiles that he comes up with are different. Well, doesn't show them here. But here they are. Well, let's count the tiles. There's this green triangle, or star thing. So that's 1. The red pentagon is 2. The blue pentagon is 3. The gray pentagon is 4. The yellow doodad is 5. And the bluish part of a star is 6. And I am just guessing that these pentagons are really exactly the same as each other, but they're colored differently, and there are some rules for what colors are allowed to exist next to other colors in order to get this irregular pattern. However, Penrose then found a way to do it with a smaller number of tiles, and that is exhibited here. There are 2 tiles here. There's this kind of maroon tile that I'm tracing out with my mouse. And there's this other beige tile that I'm tracing out with my mouse. And those are the only 2 tiles that are here. And you can kind of see that it's this, there's repeating stuff, but it's kind of a vaguely irregular pattern. Now this story is going to transition a little bit into my own hacking on this. I wanted to be able to scroll around and explore this pattern. And this, you can do that. You can scroll this, and when I release the mouse, it's going to fill in the rest that was there. But it takes it a moment to do that. I discovered, I discovered graphics cards. I knew they existed, but I re-implemented it in WebGL in a shader, and it goes much faster. But this particular set of tilings with these two shapes aren't in the WebGL thing. There's a different set of two shapes, these ones. You can see that this pattern is kind of vaguely similar to this pattern. They both have 5 symmetry, you might say. I mean, it's like from the center, if you take these pie slices that go out forever, those pie slices are the same as these pie slices here. But the stuff that happens in the pie slices is irregular. Anyway, there's a mapping from these two tiles to these two tiles. And these ones are called P1 tile, Penrose tiles, the P1 type of Penrose tiles, where there's 6 of them. And then he refined it to these ones. Now, just to get back on the previous story of how ridiculous the path is towards what's going on, which we'll get even deeper into in a moment, these 6 tiles are, these are more complicated tiles than these tiles, which is just 2 of them. And also these tiles are more complicated, I mean, in my eye, they're more complicated because one of the tiles is concave, whereas these tiles, both of them are convex. Convex meaning that if you put a rubber band around it, it would be snug all the way around the shape. These are, they're called rhombuses or parallelograms. They're one of the elementary school shapes. Anyway, it turns out that in order to scroll around this pattern, you want to figure out what the pattern is in any particular place, that there's a way to do it, and the way is kind of interesting. And I'm going to move this slider that's at the bottom, and I'm going to drag it, and as I do so, the pattern is going to do a kind of strange thing, which I'll try to explain. As I drag it, it starts to separate. And as it starts to separate, the pieces get smaller, and soon here you'll see fading in to existence some lines. And the lines are parallel lines, and there are 5 sets of parallel lines. You can kind of convince yourself that that's true by looking at the center here, which creates a pentagon. And each edge of the pentagon, there's a line that extends all the way flush with that edge. And that line that goes all the way flush with the edge, you can kind of look over a bit, and there's another one that's parallel to it. And it repeats at a regular interval. And so there are 5 angles, you might say, that these lines go at. And every time those parallel lines intersect, there is a rhombus for that intersection. And the way that the rhombuses relate to each other in the parallel lines tells you how they relate to each other in the final result. If 2 rhombuses are intersections which are adjacent to each other in the parallel lines, then those rhombuses will be adjacent to each other when the rhombuses get big. And also, I mean, kind of by extension, the hollow spaces between the points, every thing that is a hollow space between the points will wind up becoming a point, you might say. It'll be the point where all of the rhombuses that kind of make up the points around the edge of that area, all of those rhombuses will come together and there will be a point at the intersection of all those rhombuses. There are 3 of these, so the point will have 3 spokes coming out of it, and you can see how it's going to happen. So there's the point right there. These 3 spokes are coming out of it. Anyway, so this thing right here, which has 5 rhombuses next to it, is going to have to kind of expand, you might say, into a region that has 5 points around it. We can watch that happen. Oops, that's not what I wanted. Okay, there it starts to expand out. You can start to see the parallel lines. And here's that region that has 5 points around it. Anyway, so the lines tell you where the rhombuses go. Kind of. You can see that the rhombuses kind of move a bit in order to get snugly into place, but the lines tell you which rhombuses connect to which other rhombuses. And they also tell you what orientation the rhombus will be. There's also, I had meant to mention it first, there's an interesting sense in which you can see the lines in this pattern. Every parallelogram, every rhombus, is the intersection of 2 lines, and one of the lines, this rhombus here, we can consider a line that goes to here, and then to here, and then to here, and then to here, and then to here. And it turns out, because these are parallelograms, meaning that the opposite sides are parallel to each other, that when we go along one of these lines, these lines are always parallel. So in a sense, it kind of traces out a line where all of the little speed bumps that we're hitting are at the same angle. And that line that we're tracing out will be associated with an actual line when we drag it out like this to where the lines are. Anyway, so if that weren't interesting enough, it turns out that there is a parameter that you can play with that, like these parallel lines at the center here, there's just some arbitrary distance between, like why don't all 5 of these lines exactly hit the center? We could make them so that they did. And here is an instance of that. This is expanded out a bit, and you can see the edges. Just to make that more well. Oh shoot! As you can see, I mapped this thing at the bottom to do a different thing than it was doing before. Before, it was saying how big these rhombuses were. But now what it's doing is it's adjusting the phase of those lines such that if we drag it all the way to one end, then all of the lines will meet at the center. I think that we should see the same thing over here. Yeah. And all of these kind of patterns that it creates along the way, you can see that it kind of changes. You can kind of see flashes of lines that go through it, where parts of the pattern will stay the same, but some parts of the pattern along certain lines will become different. And this pattern that we're looking at right here has a thing in it which never appears in this pattern. This pattern here, the pink guys that are the elongated rhombuses, you'll never see those elongated rhombuses form into one of these star shapes that you're seeing here. These are the same two rhombuses. It's just this pattern is a derived, similar but not quite the same version of this pattern. They're actually discussed on the Wikipedia page. It shows examples of them here. These things are, I mean, I don't know that I'm generating them in exactly the same way, and I'm pretty sure these are the same things. You just look at them; it's clear that they're the same patterns that are being created here. And there's just a certain spot. It's about, I mean, it's 0.2. I don't know. I just 0.2 happens to be 1 divided by 5, and there are 5 dimensions. And I kind of played around with some numbers, and that number works. And by 0.2, I mean if this is 0 over here and this is 1 over here, then wherever 0.2 is, if we could get it at exactly 0.2, which I've just kind of, actually I think I can. I remember these things here are showing me where this is at. I take that back. Those numbers are showing something else, because those numbers will change as I move. If I could get it to 0.2, then we would see this pattern emerge, which is just a variant of this that's pretty darn homogeneous. You can see that different versions of this have different levels of homogeneity. In this one, you can see there's very distinct lines that go through it, whereas in this, that doesn't happen. There aren't lines that go so strongly as this. Anyway, that's almost it. There's one other way that I have discovered to enhance this pattern, or do a weird thing. I don't know. I'm sure people have done this. But so somewhere here we have some code that defines some parameters. These are the dimensions. There are 5. I mean, it's a 2-dimensional thing. The sense in which there are 5 dimensions is that there are, like we look at the star, there are 5 arrows, you might say, coming out of the star. Each of those is a direction, and we're calling those directions dimensions. We could say directions here. Anyway, if we make this a number like, well, I don't know what's lots of things to interest. Let's do 4 first. If we do 4, what we'll get is this is actually not what I expected. I was kind of expecting that we would see just a grid of squares without these anomalous. Okay, it has to do with where this bar is dragged. If we let's modify the code slightly with respect to what dragging that slider does to make it so that it works as it did before, to allow us to make the I have partially dragged the window. There we go. Okay, we can make these things smaller and share the grid. So that's 4 dimensions. 5 dimensions is what we were looking at. 6 dimensions. Here's 6 dimensions. There are, it's sort of what you would expect. I mean, what somebody would expect here. There is hexagonal symmetry here, as one might expect. Let's sort of zoom in. When I click, it changes the colors. There are no triangles here, interestingly. These are rhombuses. And it makes sense because the pattern demands that there be rhombuses wherever you have the intersection of lines. Anyway, we can do 7. And here's 7. I think that this is crazy interesting, and I have never seen it on the internet, but maybe it's there somewhere. Anyway, it's the same idea. You have seven sets of parallel lines. And at every intersection, there's a rhombus that will be created. And it will join with the other rhombuses according to where the parallel lines, according to how the intersections of parallel lines link together. In this case, there are 3 different kinds of rhombuses instead of just 2. And the reason is that there are 3 different angles that the parallel lines can intersect at, whereas in the case here, there are only 2 different angles that the parallel lines can intersect at. You'd have to kind of brute force it to prove to yourself that it's true, but looking around, you'll either see this kind of fat intersection, which is associated with the fatter rhombus, and you'll see an intersection which is a tighter intersection, or, well, tighter but also thicker. We'll find one of them here somewhere. Okay, here's one. These 2 guys are coming together at a pretty steep angle. Of course, these 2 guys are, there's a very thick angle here. Wherever there's a thin angle, there's going to be a corresponding thick angle. So the ones that, if you look at any angle and you look at the smaller of the 2 angles and compare those to each other, you'll find that you'll only ever find 2 such angles. You'll find this one, and you'll find this one. In the case of 7 sets of parallel lines, it turns out that there will be 3 angles that they will intersect at. And that gives you the 3 different rhombuses. One thing that I was kind of fascinated by is to discover that doing 8 dimensions does something cool rather than boring, because I thought it would be like square tiles again. But it's not. Look. It is, I don't know, it has a certain, it's intense. It has a certain 8-ness to it. A lot of, there are squares and there are tiles that are, there are only, I'm pretty sure, I've looked at it, I'm pretty sure there are just 2 kinds of tiles, or there should be 2 kinds of tiles, but the way that the algorithm that I use to distinguish the tiles is not perfect. I don't actually do it based on the angle, I do it based on some other sort of numerical formula that I came up with that works for odd numbers, but not for even ones, because I didn't think there was any interesting things that could happen in the even ones, but clearly there is. But in any case, so it looks like there are like 3 different colors here to me, maybe I think 3, but there should only be 2, because there are only 2 kinds of tiles. But I think there may be some interesting meaning behind the different colors of the same shaped tiles. I don't know. Anyway, it looks pretty cool. We can do 9. We can do. I've done up to 13, I think. Here's 9. I don't know whether to be embarrassed about this or, I mean, this is a graphical anomaly. It has to do with floating point precision errors. My guess is that this particular floating point issue could probably be resolved. This code is currently, I'm pretty sure it's using 32-bit floating point precision on the graphics card. Graphics cards these days can do more. I'm not sure that WebGL can do more. But even without that, there are plenty of tricks to be played in dealing with that, but I failed in this instance. Anyway, that's what's going on there. What's happening is that there are more than two lines coming together at a point that's pretty darn close, and it gets confused about what tile should be there, because there are more than one line meeting at one point, which should never happen. Only two lines should meet at any particular point. Anyway, so here's the pattern. I don't know if I've tried, I think I've tried 10. Ooh. Yeah, that's nice. I like it. With these kind of weird circular things every so often. Those circular things, I always find playing with this slider that you can kind of see some, I mean, I can, I find that there are interesting things to behold in the lines themselves, if there's a weird kind of thing showing up in the tiles. I mean, makes sense. It's just very cool. Okay, here's 11. I'm going to do it up to 14, and then I'm just going to stop the video. That's pretty cool. 12. Kind of like the even ones. They have, I feel like they do. I feel like the even ones have kind of an interesting blend between normal sorts of symmetry and weird sorts of symmetry, whereas the odd ones just have weird sorts of symmetry. It's kind of interesting. Well, here's 13. There's definitely some kind of eye here, and I feel like as the numbers increase, that as you go away from the center, there's just a lot of craziness, but sometimes you can find. Let's see. My guess is that if we kind of scroll around it, we'll find another glob of interesting apparent symmetry. I saw something down here that looked like, I don't know, that kind of sticks out at me, this blob right here. So I feel like I can kind of see another, my guess is if we look at the lines, that we'll find here you can actually see there's a thicker band of separation here than like, here's a maybe as thick. It's pretty thick as we go. Yeah, I mean, it's a relatively small difference, but there's also these clusters, but this particular cluster to my eye, has a much higher ratio of stuff in the center and much whiter, cleared out pool around it versus this one, which is fairly tight center, fairly cleared out, but there's some stuff in there. There's some stuff in this one. This one has some stuff, but not nearly as much as these ones. Anyway, that's 13. We'll do 14, and then be done with it. Oh, I'm glad I did 14. That's beautiful. Well done, math. Okay. Great. Where's my thing? Okay.